Okay guys, this is like the third time I've started this video because I can't talk, I can't write. It's like 5, oh my gosh. Yeah, it's almost 6 on Friday night. So bear with me, this is the last time I'm doing this, so any like dumb things I say or any terrible handwriting mistakes I make, I'm no longer caring. So, I need you to get these notes down, guys, because when I come back on Thursday, I'm going to assume you understand and can do and have notes on all of this stuff. Okay, these things that you take notes on today and tomorrow will be on your 9 weeks test, which is on Monday, March 4th. This unit is Unit 10, Gas Laws, and we're going to be doing a lot of calculations, okay, about how gases behave and are affected by different variables like pressure, volume, temperature, and quantity, or moles, okay? Before we talk about any of this, though, you need to understand this thing that we call kinetic molecular theory. You'll see me abbreviate it KMT a lot, okay? It's about the way that ideal gases behave, okay? Some assumptions that we make about a gas. If it's an ideal gas, it can technically be about solids and liquids too. Okay, so these assumptions that we make, these postulates for kinetic molecular theory, is that the gases consist of tiny particles, right? And you know those particles to be atoms and molecules. Okay, we assume that these particles are so small their volume is negligible. Okay, and this word means pretty much zero or nothing. Okay, we assume that these particles are in constant and random motion. Okay, and that in this constant and random motion, they're bouncing around all over their container, and they are colliding with the walls of the container. This is super important. Okay, when they collide with the walls of their container, this causes the pressure exerted by a gas. Okay, so anytime you feel a high pressure, that's because apparently for some reason, whether it's a smaller volume or a higher temperature, the gas particles are colliding with more force and more energy and more speed and more frequency. They're colliding with the walls of their container. That's a higher pressure. Okay. The fourth assumption that we make is that we assume these particles are assumed not to attract or repel each other. Okay, again, we're talking about ideal gases. In real life, you remember from last semester, we talked about all of those intermolecular forces with those attractions and repulsions, no matter how faint they may be. Okay, the fifth assumption that we make is that the average kinetic energy and I abbreviate that KE, is directly proportional to the temperature, and we measure temperature in this weird unit called Kelvin. We'll talk about it more in a minute. Of the gas. Okay, so let's talk for a second more about ideal gases. You need to be sure you understand that an ideal gas is very different than a real gas. Okay, so ideal gas behavior is what we just described with the kinetic molecular theory. Okay, they really only behave this way. Ideal gases only behave as an ideal gas. So what we wrote down up here, under these conditions, very high temperatures, okay, and very low pressures. Okay, at a very high temperature, they are going to have so much energy. They're going to have a high enough energy, right? Because remember, temperature and energy are directly related. They have a high enough energy at a high temperature to overcome any attraction and repulsion that they may have. High enough energy to overcome attractions and repulsions. Okay? And at very low pressures, they're just so very spread out that they're not attracting and repelling each other because they're like so far away from each other. Okay? So let's talk a little bit more about pressures, and I'm going to go to my next page. If you've got room to keep writing, you can. Oops. Oh gosh, I hope I didn't just mess the focus up forever. Yeah. This is just so fun. I love this when it happens. You guys are so smart. You're probably like, just press this button. I'm just not finding it. There. Okay. Okay, so pressure. Again, write this down again. It's this important that I want you to write this down again. Pressure is exerted when the gas particles, my lights, collide with the walls of the container. Okay, there are 3 units of pressure, and you need to have these memorized. Okay, units, memorize. Your units are ATM, that stands for atmospheres. mmHg, that stands for millimeters of mercury. kPa, that's kilopascals. And there's another one that you don't have to memorize, but I'm going to tell you anyway because it's a common one that you've probably heard before. PSI, pounds per square inch. Okay. Not only do you need to have the units memorized, but you need to have these conversions memorized. 1 ATM equals 760 mmHg equals 101.3 kPi, and just for fun, 14.7 psi. But again, you don't have to memorize that one. But you have to know 1 ATM is the same thing as 760 mmHg, millimeters of mercury, is the same thing as 101.3 kPa. It's just the same thing as saying like 1 gram equals 1,000 milligrams. You know, they're just conversions. Okay, so we may have you convert these in and out of these units. Like I may give you a problem in ATM and expect your answer in millimeters of mercury. Okay, so if you're doing conversions, you're just doing really simple dimensional analysis. Okay, like baby dimensional analysis. So let's do a practice problem. Convert 0.927 ATM to millimeters of mercury. There's your given. So 0.927 ATM over 1. Set up your next conversion. Drop your units. I want mmHg. And then you plug in your conversions, right? Just like 1 mole equals Avogadro's number, 1 ATM equals 700 millimeters of mercury. 1 ATM, 760 mmHg. And then you just plug it into your calculator. I should have had this down already, but I didn't. 0.927 times 760, 704.52 mmHg, and we're not going to stress about sig figs until the end of a math problem because you're just going to be doing this in the middle of a problem, but technically it would be 3 sig figs, so 705. I'm going to set a good example for you. Let's do another one. Convert 0.927, I'm going to say kPa to ATM. Okay, so take your given and put it over 1. Set up a new conversion, drop your units, put what you want on top, and plug in your conversions. 1 ATM equals 101.3 kPa. 0.927 is going to be a really small number. Divided by 101.3 equals 0.00915 ATM. Okay? So you're going to have some, if you check It's Learning on the agenda for today, there are some pressure conversion problems I want you to do with a key. The other variable I want to talk about today is temperature. Okay, we can't use Fahrenheit or Celsius for these problems because we need, oh my god, I told you I can't write. We need a temperature system with no negative values. Okay, so we use Kelvin, and we abbreviate it with the letter K. Okay, that is just equal to degrees Celsius plus 273. So whatever degrees Celsius you have plus 273 equals your Kelvin temperature. Okay, 0 degrees Celsius would be 273 Kelvin, right? 25 degrees Celsius would equal 298 Kelvin. Negative 273 Celsius would equal 0 degree Kelvin, and this is what we call absolute zero. Okay, the last thing that I'm going to have you jot down during this video notes is STP. STP stands for Standard Temperature and Pressure. And you need to know that that is 0 degrees Celsius, so 273 Kelvin, and 1 ATM. Or if you're working with a different unit, then it would be 760 mmHg or 101.3 kPa. But 1 ATM is just like your super conventional, universally accepted standard pressure. Okay, so you got to know that because there's going to be some problems where that's how we give you your pressure. Your pressure and your temperature. We're just going to say at STP, and that's us telling you 1 ATM and 273 Kelvin. Alright guys, so check It's Learning, check that agenda. There's some problems I want you to work, and then there's a couple more videos that you're going to watch for tomorrow with some more problems, and then I'll be back. Alright, have a good day.